Lab 4, Spring Force and the Energy Principle by Veronica LeBlanc. Objective. The objective of this lab was to analyze the motion of a spring in terms of the energy of the system by first reviewing real-time data from Tracker, then finding the period, spring constant, and original spring length using this data, then comparing the periods of the X motion and the Y motion along the spring by then modeling this motion in VPython and finally analyzing the total energy of the system. Here are some of the physics principles that you will encounter during this lab. The energy principle is probably the most crucial one, the biggest reason that we're doing this lab, and this principle states that the sum of all potential and kinetic energies is equal to the total energy. So in this case we have the gravitational potential energy, the spring potential energy, and the kinetic energy of the system. Another important principle is the period of oscillation, which is T is equal to 2 times pi times the square root of the mass of the object over the spring constant, where the spring constant is equal to, conversely, 4 pi squared times the mass of the object over T squared. In this particular experiment, knowing the formula for the spring constant, deriving it from the period is important because we don't know the spring constant initially. However, we can derive the period from our data in Tracker. The next physics principle it's important to understand is Newton's second law, which states that the sum of the forces, implies that the sum of the forces in the system, if they're equal to 0, must mean that the sum of the forces are equal to 0, meaning you can set up an equation such that the force of the spring is equal to the negation of the force of the gravity in this particular instance. Hooke's law is the final principle that's important because, of course, we're dealing with springs. Hooke's law states that the force of the spring is proportional to the difference in length of the spring, how far it's moved from its natural length. And we can derive what our original length was, which was an unknown, by using this formula. This is the data that I got out of my Tracker model, which I will show here briefly. Here you can see on the right side of the screen that the period is pretty consistent. The motion of both the X and the Y is oscillating. Now back to here. Here's giving you an idea of what my calculations were, how I derived the different formulas for my particular model. The final spring constant that I arrived to for the Y direction is 6.869, and the initial position of the string I calculated be 0.126. This is what my model looked like when I did it in VPython. This is the graph that I got. As you can see, the amplitude is a little larger than the predicted right here. I am not exactly sure why that's the case, but the period is identical, and this is modeling the motion pretty similarly. Here is a picture of some of the screenshots themselves. Here you could see there's kind of a Lissajous pattern with the motion of the spring. The black line here is the force of gravity, and the blue line is the force of the spring. Now to analyze the energy overall. As you could see, the energy is negative, so according to what my model was predicting, this is a bound system because the total energy is negative, sums to be negative. The red here is the kinetic energy, and the green here is the potential energy, which is negative. Now to compare the periods, we have the Y period, which was equal to 1.52 seconds, and the X period, which was calculated to be 1.61 seconds. As you can see, the X period is longer than the Y period down here. This is because the bouncing motion was, the up and down motion rather, was occurring more frequently than the left and right motion. Overall, the energy principle was important, and well, this system did utilize it. Thanks for watching.